This is the audio-based object recognition MQP. Our project began by asking if there's a way to distinguish between hollow areas. For instance, is there a simple way to determine if a tunnel is cracked, blocked, or eroded? Or is there a way to learn about the maintenance needs of factory equipment such as pipelines? Or on a smaller scale, is it possible to determine the health of mechanical components inside a factory such as screws, bolts, and nuts? And if there is, can a similar technology be applied to monitor small enclosed spaces like the health of a human ear? The answer to these questions is yes. These tasks can be performed through a combination of audio signal processing and machine learning. But that leaves the question, what makes audio so special compared to other modeling methods such as LiDAR, sonar, and cameras? Other modeling techniques require rotation, specialized equipment, and are suited for certain environments. Additionally, they can potentially harm humans. An example of this is sonar. Sonar is great for underwater applications, however, is limited in the air.
Our method uses a 4-microphone square array connected to a Raspberry Pi with a central speaker emitting sound. The microphone captures audio signals reflecting off the environment, and over 20 features are extracted and fed into a machine learning classifier as training data and testing data. The features are first plugged in individually, but then they are combined to improve the algorithm performance. In this case, the setup is being used to determine which of the 3 shapes covers the microphone array. Three experiments were conducted to show the potential of audio classification. These experiments were shape classification, detection of deformation, and location of deformation. First experiment, under ideal conditions, the best results of 90% accuracy in differentiating a cube, pyramid, and sphere was achieved using 8 different combinations of features. However, when the first experiment was performed under non-ideal conditions, with varying background noise, shape heights, and setups, the best accuracy achieved was reduced to 70% using zero crossing rate, acoustic loudness, and GTCC. The introduction of robustness significantly lowered the accuracy. The second experiment was differentiating between an obstructed and non-obstructed cube. The height accuracy of this experiment was 100%. This was achieved with 3 different combinations of features. The third experiment was figuring out if the left, right, back, or front of a cube was obstructed. The greatest accuracy was 90%, which was obtained using zero crossing rate, acoustic loudness, and spectral entropy as the machine learning classifier inputs. The best result of the first experiment under ideal conditions was 90%, and under non-ideal conditions was 70%. The best result of the second experiment was 100%, and the best result of the third experiment was 90%. The full list of results using individual features, multiple features, limiting microphones, and applying localization techniques can be found in the report. The overall price of our project was around $200. This is a small price to pay given all the potential applications such as factory maintenance and health monitoring. Thank you for your time.